So very happy to have amazing Vaidya, from Amazon here to talk to us about his research filters. So Kapil graduated from MIT a couple of years ago. 1 year. 1 year ago, he's an applied scientist in Amazon working on taking these ideas of building new systems in production in Amazon. And we're very happy to have him today with us.
Thank you, Mark. Yeah, so my name is Kapil Vaidya, and today I'm going to be talking about a data structure SNARF that can help you speed up your databases. Now, we refer to SNARF as a learning enhanced range filter. We use learning enhanced because SNARF internally uses some simple models within its design that improve performance. So before we get into what the details of SNARF, let's look at what range filters are. So filters are data structures that represent a set and can answer approximate membership queries on this set without any false negatives. So the two important properties over here are that they approximately answer membership queries and they have no false negatives. So let me explain this through an example. Let's say we have a set of billionaires and a filter representing this set. Now, if we ask, is Jeff Bezos in this set of billionaires? Since Jeff is a billionaire, the filter will say yes with 100% probability. So this is what I mean when I say there are no false negatives. If something is in the set, the filter has to say yes. Now, if you ask the filter if a poor grad student like me is in the set of billionaires, the filter will say, "Ha, nice try," and reject the query with a very high probability. And this is the right thing to do over here. But it might also accept the query with a small probability. And these kind of errors are allowed in filters. And the error rate over here is also referred to as a false positive. Now, these filters are quite commonly used in a lot of data systems. So in systems, as the size of the scale of the data grows, we cannot fit all of it in the local memory. So most of it gets stored on a slow storage device. So here we have a key address data set stored on the disk. Now, whenever the system gets queries, the way the system answers them is by going to the disk, scanning the corresponding data, and then returning the result. So for the query over here, addresses of keys equal to 10, the system will go to the disk and return 123rd main state as the answer. Now, some of the queries might be empty. What I mean by that is, the queries might not have any data corresponding to them on the disk. So even for these queries, the system will need to go to the disk, scan the data, and just return an empty result. So empty queries result in a lot of unnecessary disk scans. And this problem is really bad in systems where the data is divided up into multiple blocks. And the system basically answers the query by reading all of the blocks, but most of the blocks may not have data corresponding to them in there. So in systems like these, the system ends up doing a lot of unnecessary block reads, and filters can be really useful in this particular application. So what the system can do is it can store one filter per block in memory, and essentially all the queries can first be directed to these filters, and only when the filters say yes do we go and read the corresponding block. So this way filters can help avoid a lot of unnecessary block reads. Now, given this use case, filters have been implemented in a lot of production systems like RocksDB, LevelDB, Cassandra.
Why would you query a key that doesn't exist in the block? Or is it just that you want to know which block it's in?
Basically, we want to know the address corresponding to that key.
Right.
And it might be there on only some of the blocks and not all of them. But we don't know which block it is in.
So you don't want to maintain the metadata about which block everything is in, and instead you want to just query and get a.
Yeah. These filters are essentially the metadata that we are maintaining.
No, I mean, you can maintain metadata about what's in each block as well. You could do a distributed hash table. I mean, there are techniques.
Okay, distributed hash tables end up taking a lot more memory, and filters are much more succinct than them. And memory is like the precious resource over here, and that is what we are trying to save on. And explicitly maintaining like a distributed hash table for like a billion keys is not like a good method memory-wise. So filters are much smaller than that.
I'm still not quite following, because I could just do a hash to decide which block each one goes into. And that way I don't.
So the hash table ends up taking, let's say, 128 bits per key, that much space. And a filter can.
Okay, well, let's go on, we'll talk afterwards.
Oh, okay.
Yeah.
So these production systems also support range queries, which are queries such as are the keys in the range, particular range 10,15. And the filters that are implemented in these production systems do not support range queries. So what ends up happening is the system bypasses them and simply reads all of the blocks. And we have the same problem where we are doing a lot of unnecessary block reads. Now, this in today's talk, what we'll focus on is filters that can support range queries and that can avoid us help us in avoiding a lot of unnecessary block reads. And the range queries that filters will support will be of the font is there key in the range A, B. Now, given the application, what we want from these filters is they should make as few mistakes as possible so that we don't have to read unnecessary blocks. The second thing is they should be quite compact. They should since they are stored in memory, we don't want to waste a lot of memory, so they should be as small as possible. And they should be quite fast. It should be faster than the slow device access that we are trying to avoid. So generally, the filters are quite fast. So the main trade-off turns out to be between the space used by the filter and the false positive rate of the filter. So this is the main trade-off that we'll be looking at. So hopefully the functionality of these range filters are clear and like where they're applied is clear. Now suppose as a systems developer, you go to the market to find a range filter for your production system. The first range filter that you'll find is Rosetta. And if you implement it within your system, you'll find that it works really well for point and short range queries. But for long range queries, the performance is quite awful. Now, in order to understand this, you dig deeper into what Rosetta actually does. So what Rosetta essentially does is it takes a range query and converts it into multiple point queries and then uses a point query filter for it. So a range query, is there a key in the range 10, 20, essentially gets converted into point queries. Is there 10 in the range? Is there 11 in the range and so on? And then you use a point query filter for it. Now, for this particular range query, the false positive rate is actually 10 times worse than the false positive rate of the point query filter. And this problem gets even worse as the range queries become larger and larger. So since Rosetta is not the perfect solution, you keep on shopping and look for some other range filter. The next filter that you'll find is CERT. And since you were burned by your past experience, this time you look into what the filter actually does. So what CERT does is like it looks at the binary encoding of the keys and essentially stores them in a trie format. Now this trie format essentially can support range queries. And in order to save space, it only stores a prefix of this trie, not the entire trie. So this sounds like a reasonable idea and you implement it in your system. And it also works well for long range queries. But what you observe is it's not a great solution for point and short range queries. And the reason is that the encoding scheme that's used to store CERT is quite inefficient. Well, this experience leaves you a bit upset because there's no filter that's good for all of the use cases. But you don't have to worry about this anymore. Now we have SNARF, which is good for both point queries and long range queries. And the way SNARF is able to achieve this is because it's designed with space efficiency in mind. So it's able to use it's similar to CERT, but it keeps space efficiency in mind. So all of its components are quite subspace optimal. So it ends up being better than sum. Let's get into details of what SNARF actually does. So the main idea of SNARF is to map keys to a smaller domain to save space. So let's say we have a set of keys 250, 500 and 750. These keys belong to a domain of size 1000. If we were to explicitly store this set of keys, it will take 3 log of 1000 bits. And we can simply answer all the range queries on this exactly. So if there is a range query, is there a key between 550 and 600? You simply go to the array and check if there's such a key. And since there is no such key, you return no as the answer. Now, in order to save space, what we can do is we can map these set of keys to a smaller domain. So here we use a simple mapping function divide by 10. And the map values would be 25, 50 and 75. And they'll be in a domain of size 100. And if we were to store these map values, it will only take 3 log of 100 bits. So here what we are seeing is mapping things to a smaller domain saves space, which is quite obvious. Now we can also answer range queries on this map set. What we can do is we can map the endpoints of the range query into this new domain. So the new values become 55 and 60. And then we can simply go and check in the set if this such values exist. Since there's no such value, we return no as the answer. So this way we can save space and also answer range queries. Now, can we use any mapping function for mapping things to a smaller domain? The answer turns out to be no. To ensure that there are no false negatives, the function has to be monotonic. Let me show this through an example. Let's say we have this range query, is there a key in the range 450, 550? Now, 500 is actually there in this range. Now, if we were to use a non-monotonic function that maps 500 to 50 and 450 to 55, what will happen is in the map domain, the key won't be in the range anymore. And what we will end up having is a false negative. So what we show in the paper is that this condition of function being monotonic is necessary and enough to have no false negative. So the high level idea behind SNARF is that we map keys to a smaller domain in a monotonic way and simply store the map values. So mapping things to a smaller domain helps us save space, and using a monotonic mapping ensures that there are no false negatives.
This is the hash table.
Hash table. So SNARF basically has two important components, the function and the mapped value set. Now the key to SNARF's performance is actually in the details of how we design this function and how we store this map value set. So the three key contributions that help give SNARF its performance is which mapping function should we use to ensure a good performance. The second is how to efficiently approximate this function, because the optimal function turns out to be quite complex to solve. So we need to efficiently approximate it. And the third key contribution is how do we efficiently store the mapped values and how can we efficiently query them as well. So in the talk, I'll go over what design decisions we make for each and one of these single questions. And these are the key ideas in SNARF. So what mapping function should we use? I'll give an example of how using a simple mapping function actually can be quite suboptimal. So let's say we have a set of keys, 8 keys. The first 4 keys are located twice close to each other, 10, 20, 30 and 40. The next 4 keys are quite spread out, 200, 400, 600, 800. Now, if we use a simple mapping function, divide by 10 to map this set of keys to the new domain, what would happen is the keys in the orange domain will get mapped to consecutive values, and the keys in the green domain will have some space between them. Now, any query from the green domain will be able to answer it decently well. So let's say there's a query, is there key in the key equal to 235 in the set. We'll check if 23 is there in the set and we'll answer no since it's not there. But any query from the orange region, we won't be able to answer it accurately. So let's say there's a query, is there key 12 in the set? Now when we map it to the smaller domain, we get value 1 and we check that actually 1 is there and we return yes as the answer. So what ends up happening is all the queries in the orange domain end up being false positives and the error rate for this particular region is 100%. So in the future, if there is a workload which is super skewed and all the queries fall in the orange region, what ends up happening is we have a really bad false positive rate for SNARF. So given this, what is the good mapping function to map the values? Well, it turns out that if we don't know the distribution of the queries, the best thing one can do is to give equal amount of space to both the keys in the orange region and the green region. This is because if in the future there's any workload that is skewed towards a particular region, both of these regions will have a decent false positivity. Now, a function that can help us achieve this is actually the CDF of the data. So CDF of the data is the proportion of keys smaller than this particular key. So the ideal function that we are looking for is simply the CDF of the data multiplied by the size of the smaller domain. Now, the CDF of the data actually can be quite complex, and storing it in a space efficient manner and also being able to query it efficiently can be quite hard. So this is the reason why we need to approximate this particular function. Now, it turns out that approximating CDF functions has been the favorite pastime of database researchers for the past few years. So there's a bunch of literature on this particular problem. And the basic idea behind these papers is just divide the set of keys into small clusters and basically learn linear regression models in each one of these small clusters. You can make these clusters much smaller to improve your accuracy. So this is a parameter that one can tune. But the reason we cannot use this approximation method for our use case is because these series of regression models are not actually monotonic. If you look at where the first model ends and where the second one starts, you can see that this particular region is actually not monotonic. And this cannot be used in our use case because then we'll get false negatives. So what we end up doing is we force the models to end at certain points in the space. So we first pick which point should these models end at, and simply build lines between these keys. These are known as interpolation models. So in SNARF, we use a series of interpolation models instead of using a series of linear regression models. And we can ensure that this series of interpolation models is monotonic. And this set of models actually turn out to be quite compact as well. So we end up using less than 1 bit per key. So the space overhead of this model is actually quite small. So moving on to the third question, how to efficiently store and query these mapped values. So in the example before, we explicitly stored the mapped values, which can be quite inefficient. So in order to improve the storage efficiency, we store the deltas between consecutive keys instead of the keys themselves. So for example, if this is the set of mapped values, the domain size is 100. So explicitly storing them will require 5 log of 100 bits. But what we can store is the first key, then the difference of the first key and the second key and the first key. Similarly, difference of the third key and the second key. And now this delta array can be used to explicitly reconstruct the original array. So it carries all of the information that we need. But the interesting thing is the average value of this delta array would be around 20, which is smaller than the previous array. And this array will end up taking around 5 log of 20 bits to store. So this is the main idea behind how to improve the space efficiency. And SNARF particularly uses Boolem delta coding for storing these map values, which is the theoretical optimal space optimal coding for a particular use case. Now, one issue with delta coding is that decoding it can be quite slow. So let's say if we want to decode a key which is towards the end of the array, we need to read all of the initial deltas in order to reach the end. So let's say if you have a query, is there key between 70 and 72? We have to read the first 4 cells in order to answer it. And this can be quite expensive if your array contains like millions of values. So we use a simple systems trick to make this efficient. So instead of storing one single delta code, we store multiple short segments of delta codes. Now, since we're storing multiple short segments, we also need to have an indexing mechanism to find which delta code, which segment of the delta code should we look into. So that adds a bit of space overhead, but not that much. And we end up gaining quite a lot in terms of query latency. So in this particular example, if we decided to have 2 delta codes instead of 1, we can start the first delta code from 0 and the second one from 50. And we'll have these 2 short segments of delta codes. Now, in order to answer the query, what we'll need to first do is go to the indexing mechanism to see which delta code to use, and then go to that particular segment and read the prefix of that particular segment. So this way we end up scanning a lot fewer cells, and we end up gaining quite a lot on query latency. Yeah.
Forgive me, but it sounds like you're reinventing compression of monotonic sequences. I mean, there's lots of work in the information theory.
Yeah, yes. So we just use the work to make a filter that's practical. So we are not reinventing any of this stuff.
But did you look at like Elias Fano coding?
Yeah, actually we use Elias Fano encoder. Yeah. In order to make sure that we are like theoretically doing the correct things, we actually added Michael Mitzimaker to this paper.
He knows.
So yeah, so just to make sure that everything what we are doing makes sense.
Okay. Thank you.
So just to summarize, the key ideas behind SNARF is that we use a function that maps the keys uniformly in the mapped region, so that it's optimal for the false positive rate. We use linear linear interpolation models to store this function, and that we use multiple short segments of delta coding to space efficiently store the mapped values and also query them efficiently. So these are the 3 key ideas in SNARF. Just to recap, the related work that we discussed was Rosetta, which converts range queries to point queries, which is not a good idea for long range queries. We discussed SURF, which stores things in a binary trie, which is not a great idea for point queries. And our claim is that SNARF is good for both of these scenarios. Now let's look at what the results have to say. So since I mentioned the main trade-off for a filter is the space used by it and the false positive rate provided by the filter. So on y-axis we have the false positive rate of the filter, on x-axis we have the space used by it. What we want is a low false positive rate and a low space usage. So towards the origin is better. And we look at 2 workloads, one for point queries and the other one for range queries. Now, these results are on a synthetic workload where we have normally distributed keys and exponentially distributed queries. So the query distribution is quite skewed. We already have one baseline on the figure, which is cuckoo filters, which is quite close to the theoretical optimal point filter. So now let's look at how SURF performs. So if you look at SURF's performance, it's quite suboptimal compared to cuckoo filters. This is because the encoding that they use to store this trie is actually not space efficient. But the good thing about SURF is that it's able to maintain its performance for range queries as well. Now, if you look at Rosetta, Rosetta actually performs quite similar to cuckoo filters, but its performance for range queries is quite bad, and it's worse than even SERF. And this is because it's converting these range queries into multiple point queries, which is not a good technique for large range queries. Now, this is how SNARF performs. So SNARF is able to do slightly better than cuckoo filters, and it's able to maintain the same performance for range queries as well. And overall, SNARF is able to give 40x better false positive rate than SERF and Rosetta. So, and SNARF was able to do this because we kept space efficiency in mind while designing it. So both the function as well as the storage of the map values was constructed in a way which was space optimal. So that's why it's able to perform so well on this particular trade-off. And in this particular case, SNARF only ends up using 2.2 bits per key, more than the best possible theoretical limit. So it's not possible to do much better than SNARF for this particular case, at least. Now, we also looked at performance of these filters on real-world datasets. So for this experiment, we looked at results from Facebook dataset, which contains IDs of various Facebook users. So again, we'll be comparing the false positive rate on y-axis and the space used on the x-axis. What you can see here is that SNARF actually does much better than cuckoo filters for point queries, and it's able to maintain the same performance for range queries as well. So there's an interesting reason why SNARF does well for real-world datasets. That's because there is an interesting pattern in these datasets. So the pattern is that these datasets have large empty continuous spaces. So the keys in this dataset would be, they start from 10, 50, 100, 200, and they suddenly jump to like some huge value like 10,010, 10,020, and so on. Now, SNARF is able to exploit these kind of patterns. So at a high level, what would happen is SNARF will map this range of 0 to 10,100 to a small range 0 and 1,000. But what happens internally is that it divides the space into two parts, 0 and 200, and 10,000 and 10,100, and then ends up mapping them to the mapped regions. And here you can see that the number of values that we are mapping is smaller than the values that we are mapping to. So SNARF ends up exactly storing the set of keys, and these set of keys have literally zero false positive. That's why wherever there are these large empty contiguous spaces, SNARF ends up doing a lot better than other filters. Now, if you look at the figure, along with SNARF, SERF is also able to exploit this. So for point queries, you can see that SERF earlier, which was really bad compared to Rosetta, actually is somewhat similar to Rosetta. And we tested SNARF on multiple real-world datasets. And this kind of pattern is quite common in these datasets to varying degrees. Well, when we designed SNARF, we just kept space efficiency into mind, and we have seen that it's able to do well on that regard. But how does latency of SNARF look like? So for this experiment, we have the query latency on the y-axis and bits used by the filter on the x-axis. We basically forced the filters to have a fixed false positive rate for this experiment. And this experiment had a mixed workload of point and range queries. Now, if you first look at Rosetta, Rosetta actually has a very high query latency. The reason is that since it converts range queries to point queries, the latency just keeps on increasing with the range query size, and it performs bad for this particular workload. SERF, on the other hand, is quite fast. It just takes around 500 nanoseconds.
Sorry, maybe you mentioned it because I wasn't here in the beginning, but in these evaluations, especially now that we've got nanoseconds on the y-axis, what have we done to ensure that all of these things that I'm testing is actually comparable? Like, is this all handwritten assembly that somebody's gone over? Is it C code? Like,
So basically, since we like for Surf and Rosetta, they have open sourced their code, so we just use that.
And is it C++?
Yeah, C++.
And you're using the same tool chain and all that sort of stuff?
Yeah, we use the same setup for all of these basically.
And what's the hardware platform?
It was an EC2 instance. I forget which one it was, but like it was the same instance for all of these experiments.
Okay, because one of the reasons I was just curious, given imagining what these kind of implementations might look like, the inter-instruction level parallelism at the bit level operators here could be radically different and better.
Yeah.
So I'm curious.
Yeah,
That's why the metric on the left here, I think, what it is matters and what level of concurrency is on the core itself. And you don't have to answer any of that. No, I just wanted to make sure I understood that.
Yeah.
How to interpret this data.
So I think we just trying to remember this thing that I think we had like 16 cores or something on it, and we I think enabled parallelism to do this thing. Yeah, but we can talk about this details later.
Sure.
An interesting thing about SNARF is actually when we discussed this Golomb codes, right? We said that we'll store multiple short segments. Now, depending on how short we want the segments to be, we can actually improve the latency of SNARF. We can have really short segments to have a faster inference, larger segments. But if you have short segments, what happens is the indexing mechanism actually ends up taking a lot of space. So it becomes space suboptimal. So this is what we are able to achieve. This is the trade-off we are able to achieve with SNARF. The most space efficient SNARF actually ends up taking 2000 nanoseconds, very little. But you can make it more more efficient by having smaller codes. Another interesting thing that we tried was that the Golomb code in delta coding that we use for storing the delta codes is space optimal. But can we come up with can we use some other encoding that is decently space optimal but has a better latency? So we ended up using this Elias-Fano encoding as well, which someone had already mentioned. So Elias-Fano encoding, the best point of Elias-Fano encoding is not as good as Golomb coding, but it is able to offer a better query latency and space trade-off compared to Golomb coding. So this is also like an interesting future direction, that what is a coding that will ensure better latency. Our focus was mainly on space optimality, but maybe you can choose like other encodings based on your trade-off. Now we evaluated these filters in a standalone manner, but does SNARF's performance actually translate to a production system? So we ended up implementing all of the baselines in ROXDB. And for this particular experiment, what we did was we fixed the amount of memory that all of these filters get. And we ran a workload of all empty read queries. So the idea was that if a filter is able to offer low false positive rate, we'll have lower IOs and faster execution time. So on y-axis, we have the workload execution time. And on x-axis, we vary the range query sizes of queries in this workload. Now, the first two baselines we are seeing is Surf and Rosetta. Surf in green, you can see that it's able to maintain a similar performance across all range query sizes, but it's suboptimal compared to Rosetta for smaller range query sizes, which aligns with our understanding of Surf. Rosetta gets worse as the range query size increases, so this also makes sense. Now, SNARF is particularly able to do much better than all of them for all the range query sizes. And the throughput for this particular experiment was 10x compared to other filters. Now, just to point this out, this is a workload which has all empty read queries. So production setting might also have queries which are not all empty. So this was particularly used to showcase how good SNARF is. So in summary, we saw SNARF, which is a learning enhanced range filter that provides near optimal performance for point and range queries. as well. And it's learning enhanced because like it uses simple models within it that help improve its performance. But we also use other key techniques within it, like choosing the right encoding scheme and so on, to get a space optimal filter. Now, there are some interesting extensions of SNARF. The one I'm interested in is making it adaptive to the workload. So in the current construction, we chose a function which is agnostic to the workload distribution. Now, given that we know the future workload distribution, can we choose a function which is better than the generic CDF? So that's an interesting direction. The next direction is like, can we make it faster? Space optimality was a core principle. Can we change it? Can we have latency as the principle and so on? So yeah, these are interesting directions of SNARF. And I guess we have more time now, so I'm going to plug in my other research as well. So I've broadly been working on this area of machine learning for systems. This is quite an active area of research with a lot of research papers every year. And the basic idea is like, let's try to use machine learning models to improve database or systems components. These models are able to learn the workload distribution and fit to that, or they're able to learn the data distribution, they can fit to that and improve the performance. Now, these models range from like simple models like what I use today, like linear regression models, to as complex as like DNNs and transformers and so on. My work, my contributions have particularly been adding learning to sorting algorithms, to Bloom filters, to range filters, to hash tables, and to query optimization. So this has been my general area of work. Since we have some time, I'll briefly go over this learned sorting algorithm because it's a cute technique. Now, sorting is a algorithm that we all have learned in CS 101. We have all read about quick sort, merge sort, and all of these algorithms. Now, what new idea do we bring to the table? So the new idea we bring to the table is we imagine sorting as a prediction task. So given an initial array of keys, what we are trying to do is for each one of these keys, predict its final position in the sorted array. Now, if we have a model that accurately can learn this mapping, what we can do is we can just simply scan this initial array and place keys into their respective positions and basically get a sorted array. Now, if we have a perfect model, we can sort the array in O of n time. And for this particular example, the perfect model was quite simple, expert n. So in general, what's a good model? So the model turns out to be the CDF of the data. And CDF is the proportion of keys smaller than the particular key. As we have seen before, like learning this exact function is quite inefficient. So we can use techniques from the literature to approximate it. And in this particular case, actually, this series of linear regression models turns out to be good enough. Now, since we don't have the exact mapping function, we have like this model that approximates the function. It leads to very interesting system C issues. Like the issues are that when we use this model, when we use the similar algorithm as we used before, what we end up with is an approximately sorted array. So it's not exactly sorted. The reason is that the model is imperfect. And there are issues such that the order of the keys might not be right because the model is not monotonic. And multiple keys might get mapped to the same location as well. So these are the two important issues that pop up. The way we solve it is as follows. So there are a lot of collision resolution techniques in hashing. So one of the techniques called bucketing. So what bucketing does is instead of having one slot in each location, it has multiple slots. And if multiple keys get mapped to the same location, you can use the other set. So this is how we reduce collisions. Now, still what we have is these local errors where things might not be in the right order and they might not be in the right place. in order to fix that, we use an algorithm that's able to correct these local errors quite efficiently. So something like insertion sort. And at the end, we get this finally sorted array. Now there are more details to the algorithm, which I'll just skip over in interest of time. Let's look at what the results are like. So we compared learn sort with various competitive sorting algorithms like std sort from C++, stim sort from Python, and so on. And these are the results. On y-axis, we have the sorting rate of the algorithms, and on x-axis, we have the different data sets we use. Now, yeah.
Just a question about the implementation. So, sorry, yours is learn sort, is that right?
Yeah.
Is the model evaluated on a CPU, or are you evaluating on a GPU?
On a CPU.
Okay. And
this is
size...
in-memory sorting algorithm.
Okay. Yeah, some people claim that as long as you put it on the GPU memory, it's in memory. But anyway, if you, so is the data set size here? So what kind of sizes are you talking about?
So we are talking about like 100 million to a billion.
Okay. Great.
Yeah. So by rethinking about the sorting algorithm, we are able to get better performance than the other sorting algorithms, and we can get up to like 20-30% better result compared to the other algorithms. Yeah.
What kind of keys did you get? If you took uniform keys, you're not going to get any better. No?
So
they're uniformly displaced.
Yeah.
So this is all Facebook data?
No, this is all the data sets are like shown at on the x-axis. So this is like longitude, latitude data from this OpenStreetMap data set. And then there's this data set IoT, which had like memory usage of like a lot of like servers. So this is floating.
Basically, the lower entropy the data, the better you'll learn. The higher the entropy, the more likely everything's distributed.
I think in this particular case, what used to happen was like if you use lower entropy data, actually we perform similar to others. And if you use like higher entropy, there was a larger difference.
But where is the benefit coming from? Is it because I think if I tell you right that you are doing one pass to learn some pass to learn the distribution?
Yeah. So basically
so you do two or three passes while the other one has to do an n-log-n algorithm. Is it that the benefit or something else?
So the benefit comes from the number of passes we have to do. So let's suppose we take like a 64-bit value, and if you want to sort it generally techniques end up taking 6 passes to sort. But what we can do is we can get a decent amount of sorting to a single pass, and in reality we end up doing 2-3 passes because they are more cache efficient. So the benefit that we get is that we do less passes, but each single pass of ours is actually more expensive than others because we use this like model, right, of estimation.
But the model, do you learn in your first pass?
Yeah, we learn the model in our first pass.
There's something really interesting there that you said that I just want to make sure I can restate, right? So I think one thing is that everybody's going to have to touch this data once. So
yeah.
You go ahead, and even if that pass is cache inefficient, right? Because given the sizes you're saying, they're not going to fit in an L3, you're going to chug through the data once,
yeah,
right? And it sounds to me like one of the advantages that seems to be happening, not just that you're going to reduce the number of passes, but in that first pass, you'll end up actually improving locality optimizations on future passes. That more of them will be closer in the cache reach, that will already be sorted enough, and for whatever interactions of those sort mechanisms, you're going to buy yourself a reduction in passes and a reduction in cache misses.
So this generally happens in the last few passes, but yeah, in the initial passes, it's.
But you're getting a faster jump to that stage.
Yeah, that's true.
So just want to go back because I couldn't ask my question on the previous work on the queries, if possible.
I'll just complete this and
Okay,
then
you
we
wanna
can
finish
take
this?
questions.
Okay.
Is that fine?
I thought
Oh,
it
yeah.
was there. Okay. This is-
Or we can just start taking questions. This is.
Yeah, maybe just, so like, when you build that model, how expensive is it? Like, can you talk about that or?
So it depends on like what kind of model are we building. So.
Yeah, just for the sorting model.
So for the sorting one, we end up sampling the data and building the model.
I see.
So based on how much data we sample, it gets more expensive. But generally, it's much cheaper than doing a single pass. So if you sort like 2-3% of the data and use these regression techniques to learn the model, it's
Yeah.
quite efficient compared to doing a pass over the entire.
And can you reapply that model towards?
It actually
some other type of
reapplies.
sorting?
So we use the same model again and again for all of the passes. Potentially you can sample the data again and learn new models, but we have not explored. We reviewed the model in all this.
Look, speaking to the query work, right? Let me understand correctly the workload that you have. So somewhere you have stored some ranges and then you have queries with a number and you're wondering whether or not they fall in any of the ranges that you have in your data set, correct?
So basically we have numbers in the data set and we have a range query. Now we want to see whether there's anything in this set that satisfies this key range.
Oh, I see. Okay, you have a range and then you want to see if anything in the data set. I see. And there's that.
If there's nothing in the data set that satisfies this range query, what we can avoid is we can avoid reading that data.
I understand. Okay. I see. So I mean, it seems to me that you have optimized created optimization for a sequential solution, right? But because your data set is comprised of different points that potentially you could check in parallel, right? In theory, a lot of the solutions would be amenable to parallelization, right?
Yeah, so there is still opportunity to make things parallel. Yeah, we haven't explored that. It's a single thread.
Okay. The other thing that got me thinking, right, is what about the other side of the story where you have ranges and you want to figure out if your data point falls in any of the ranges that you have?
That's an interesting question. So what do you think would be like a practical scenario where this will be used?
I don't have a practical scenario. I think of a good solution. I mean, I just say, this being a system seminar, right, got me thinking that, hey, there is potentially accelerators that we could build. They can do that very fast, but also data structures that we can reuse. In fact, our computers normally do that trillions of times per second when they check whether or not you can access memory or not, right? Essentially, all you're doing is figuring out if the address you are trying to access stays within ranges where you have permission to access. So I wonder if we can actually repurpose MMUs that you already have to offload some of these, and essentially you get an exception if you don't have, but you get a valid translation if you do have that in the range.
Yeah, speaking to that, so actually trying to bastardize the TLB
Yeah.
by manipulating what is represented by a virtual address.
You have the king of the TLB
Play with that a little bit to try to see whether we could convert basically the auto-associative memory that we already have into a fast path for doing checks like
Yeah,
that.
exactly. You don't have to build an accelerator, you just have one already on your machine.
I have you keep your hands off my TLB.
Now
Is the final output the same because you have these packets that you create? All of the other algorithms, they actually give you a sorted array, right?
Yeah.
Are you also giving a sorted array at the end?
Yeah, we also give the sorted array at the end.
And this is included in the whole latency and everything, right? Just to make sure
in
that
the first
the numbers
part,
are comparable, right? So the end result of the learned sorting should be a sorted array, not two buckets, not two arrays with.
no, in terms of memory also it's just a sorted array. We also built like an in-memory algorithm that does not use any extra memory
Okay.
over here. So we just use the initial array's memory to do this. So we have also built that, so you'll get the sorted in the same place.
Just two comments. First of all, your last sorting algorithm, I mean, that's just counting sort.
Yeah.
But that's also a basis for radix sort. So I'd imagine you could take your version of counting sort and input it into radix sort and possibly get a faster radix sort algorithm.
Basically, our algorithm is essentially radix sort, but like with fewer passes. So I guess in radix sort, you look at like the
You're doing
10
counting
bits.
sort, which is the fundamental primitive, right? You have.
Oh, yeah,
Right. Radix sort is you do counting sort on each digit, if you will, from left to right, one by one.
So in radix sort, what happens is like we look at digits from the starting
Yeah.
rate and then sort it.
From left to the.
So when we use this model, right, what ends up happening is actually we are sorting based on first 15, 16 bits. Then in the next pass, we sort based on like the next 15, 16 bits. So it ends up being like a radix sort. So it's like a mixture of the counting sort and radix sort.
And then the other question was with your SNARF. So why not use chaining just like you did in your sorting? In other words, rather than build a complicated function, to that just one pass, you can have a simpler function and then chain things that end up
So
happening.
chaining ends up being quite expensive as a technique because like we need to like allocate memory somewhere else. So that is why we pre-allocate the memory using bucketization. And what ends up happening is like even if you don't fit all of the keys that get mapped to the same place in the bucket, right? We have a spill bucket at the end where we add the keys. So but chaining as a solution is quite like it takes up a lot of time because we need to allocate some memory somewhere.
Oh, no, you can pre-allocate how much you want to allow for chaining. You can use open addresses. There are lots of techniques.
Yeah, but yeah, potentially that can be done. Yeah, with this like algorithms, you can always take a technique and try to make it work, and it's always a potential solution. We have not tried it yet, but that's an interesting thing to try. From our initial experiments, bucketization seemed more promising, so we continued with that.
So to be back off of the Hans question earlier about like building models and how much this actually costs. So if I go back to SNARF for a second as well.
Yeah.
So like excusing the fact that blue filters, you can't do range queries on them, right? Blue filters are like beautiful because they're essentially simple to build and
Yeah.
really simple to like query on, right? So SNARF is really cool because it looks like you're getting a lot more like performance during like execution time.
Yeah.
But it's common in like databases, especially if you like compact files and destroy like sets over and over, you have to rebuild these filters over.
Yeah.
I don't know if you can comment or like have any results about essentially how much more penalty do we have to pay if we were to use SNARF, right?
Yeah.
In building like these filters over and over again.
So we tested out like what is the build time of SNARF. And we did not really optimize it that much. And it turned out to be similar to the build time of SURF and like Rosetta. There wasn't much difference between them. But the reason like Rosetta is slow because like it uses multiple layers of bloom filters and it's more expensive to build. But if we compare against like point filters like bloom filters and all, there are like efficient preparation techniques for them as well. So they turn out to be much faster than any of these range filters.
I see.
Yeah. So range filters are in general like more expensive to build.
Makes sense.